Regular strongly compactness and regular strongly connectedness in topological space. Abstract. In this paper we proved that the regular strongly separated sets in the topological space. Also we extend our work in regular strongly compactness and connectedness in the topological space. Introduction. M.Karpagata and A.Pushpalati already proved the RW closed maps and RW open maps in topological spaces. Later they worked on RW continuous map and RW irresolute maps in the topological space. M.Karpagata and A.Pushpalati already proved that regular weakly separated sets in the topological space. We introduce the structure of regular strongly separated sets. Also we give the concept of regular strongly compactness and regular strongly connectedness in the topological space. 2 Preliminaries. 2.1 Definition. In a topological space X is called regular space if every closed subset C of X and the point P not contained in C admit non-overlapping open neighborhoods. Thus P and C can be separated by neighborhoods. This is known as regular space. 2.2 Definition. A topological space X is called separated if given any two distinct points X and Y are disjoint by neighborhoods. 2.3 Definition. A topological space X is called compact if every open cover has a finite subcover that covers X. 2.4 Definition. A topological space X is called complete if every Cauchy sequence has converges in X. 2.5 Definition. The weak topology on X is the initial topology with respect to dual space family X. It is also known as coarsest topology such that each element of X remains the continuous function, and this is differ from ordinary topology. That ordinary topology is called strong topology. 2.6 Definition. Let Xt be a topological space. Two non-empty subsets A and B are said to be weakly separated if an CL B equals an RWCL A, N equals. 2.7 Analogy. Two regular weakly separated sets are always disjoint. 2.8 Definition. A collection I of regular weakly open sets in a topological space X is called a RW open cover of a subset B in X if B.I.I. 2.9 Definition. A topological space X is regular weakly compact if every RW open cover of X has finite subcover of X. 2.10 Definition. A subset B of a topological space X is called RW compact relative to X if for every collection I of RW open subsets of X such that B.I. there exist a finite subset I0 of I such that B.I.IOAI. 2.11 Definition. A subset B of a topological space X is called RW compact if B is RW compact as the subspace of X. 2.12 Definition. A topological space X is regular weakly connected if X cannot be written as a union of two disjoint non-empty RW open sets. 3 Main result. 3.1 Definition. Let Xt be a topological space. Two non-empty subsets A and B are said to be strongly separated if there exist an open sets U and V such that A.U, B.V and U and V equals. 3.2 Theorem. Two regular strongly separated sets are always disjoint. Proof. Let A and B be regular strongly sets by the 3.1 definition. There exist an open set U and V such that A.U, B.V and U and V equals. This implies that A and B equals. Hence A and B are disjoint. 3.3 Example. If X equals A B C D E F G H, T equals X, C D, D F, A E, A G, B C D E, A C D U equals C D F, then the interior is U0 equals C D F, so U is an open set. Let A equals C D A and V0 equals A E G, so V is an open set. Let B equals A E B V. If U and V equals, then A and B equals. 3.4 Theorem. Let A and B be two regular strongly separated sets of xt. If CA and DB, then C and D are regular strongly separated. Proof. Let A and B be regular strongly separated sets of a topological space, xt. then by the definition there exist the open sets UV such that A.U.B.V.U.N.V equals. Let C A and D be, then we have two open set UV, then C.U.D.U.N.V equals, thus C and D are regular strongly separated. 3.5 Example. We have to follow 3.3 Example. Let C equals D. D equals E. It follows that C.U.D.U.N.V equals, thus C and D are regular strongly separated. 3.6 Theorem. Two regular strongly closed subset of a topological space, X, are R's separated if they are disjoint. Prove. If R's separated sets are disjoint, then R's closed separated sets are disjoint. Conversely, let A and B be two disjoint R's closed sets. Since A.U.B.V, then we have RCL, A, equals A RCL, B, equals B, and A and B equals. This implies that UN equals. Consequently N, CL, B, equals N RCL, A, N equals. Hence A and B are R's separated. 3.7 Lemma. If the union of two R's separated sets in a R's closed set, then the individual sets are R's closures of themselves. 3.8 Theorem. Two disjoint sets A and B are R's separated in XT, IFF. They are both R's open and R's closed in A. Prove. Two disjoint sets A and B are R's separated in XT, then N, CL, B, equals N RCL, A, N equals. Let R equals A. Then RCL R, A, equals RCL, A, N, equals, N, equals. Therefore A is R's closed in R. Similarly B is R's closed in R. Now A N equals. So A and B are complements of each other in R. Thus each one of A and B is R's open in R. Conversely, let A and B be disjoint sets which are both R's open and R's closed in R. Equals A. H equals RCL R, A, equals RCL, A, N equals. N equals A. N but A N equals. This implies an RCL, A, N equals. Now A and RCL, A, N are disjoint, and their union is R. So RCL, A, N equals N, CL, B, equals. Hence A and B are R's separated. 3.9 Definition. A collection I of regular strongly open sets in a topological space X is called a R's open cover of a subset B in X if B I. 3.10 Definition. A topological space X is regular strongly compact if every R's open cover of X has finite subcover of X. 3.11 Definition. A topological space is said to be strongly compact if every cover of pre-open sets admits a finite subcover. 3.12 Theorem. A R's closed subset of R's compact space is R's compact relative to X. Prove. Let A be a R's closed subset of a R's compact space X. Then AC is R's open in X. Let S be a R's open cover of A in X. Then, S along with AC forms a R's open cover of X. Since X is R's compact, it has a finite subcover, say G1, G2, Gn. If this subcover contains AC, we discard it. Otherwise leave the subcover as it is. Thus we have obtained a finite subcover of A, and so A is R's compact relative to X. 3.13 Theorem. A closed subset of R's compact space is R's compact relative to X. Prove. Let A be a closed subset of a R's compact space X. Then A is R's closed. Therefore by Theorem 3.5 every R's closed subset of a R's compact space is R's compact relative to X. Hence A is R's compact space related to X. 3.14 Definition. A topological space, X, is said to be regular strongly connected, briefly R's connected, if X cannot be written as a union of two disjoint non-empty R's open sets. 3.15 Theorem. Every RW connected space is connected. Prove. Let X be an R's connected space. Suppose that X is not connected. Then X equals A.B, where A and B are disjoint non-empty open sets in X. Since every open set is Rs open, A and B are Rs open. Therefore, X equals A dot B, where A and B are disjoint non-empty Rs open sets in X. This contradicts the fact that X is Rs connected and so X is connected. 3.16 Theorem. A topological space, X, is Rs disconnected if there exists a non-empty proper subset of X which is both Rs open and Rs closed. Prove. Let A be a non-empty proper subset of X which is both Rs open and Rs closed. Then clearly AC is a non-empty proper subset of X which is both Rs open and Rs closed. Thus A.AC equals. And therefore A.RCL, AC, equals. And RCL, AC, A equals. Also, X equals A.AC. Thus X is the union of two non-empty Rs separated sets. Hence X is Rs disconnected. 3.17 Theorem. If the sets A and B form an Rs separation of X, and if Y is an Rs connected subspace of X, the Y lies entirely within either A or B. Prove. Since A and B are both Rs open in X, the sets A.Y and B.Y are Rs open in Y. These two sets are disjoint and their union is Y. If they were both non-empty, they would constitute an Rs separation of Y. Therefore one of them is empty. Hence Y must lie entirely in A or in B. 3.18 Theorem. If every 2 points of a set A are contained in some Rs connected subset of A, then A is Rs connected. Prove. Suppose that A is not Rs connected. Then A is the union of two non-empty disjoint Rs open sets G and H. Let G.G and H.H. Then G and H are two distinct points of A. By hypothesis, there exists a Rs connected subset B of A such that GH.B. But B is an Rs connected subset of a Rs disconnected set A, we have B.G or B.H. Since G and H are disjoint and B contains at least one point of G and one of that of H. This is a contradiction. Hence A is Rs connected.